Okay, so today we're going to be looking at section 7.6, solving trig equations. And let's take a look. So we're going to start off by considering this equation. The cosine of x equals 1/2. And if I solve this using inverse trig stuff, I will find, when we solved from the last one, we find that I get one answer, pi over 3. Okay, so when we use inverse trig functions, we only get one solution because this cosine inverse is only defined for angles between 0 and pi. But the cosine itself is defined for all real numbers, and there should be infinitely more solutions. So let's take a look at this graph graphically. So in this situation right here, I graph the cosine curve, and I graph the line y equals 1/2, and you can see that I have many, many solutions of intersection, and it goes on forever in both directions. Okay, so we need to be able to express all of these solutions. So how do I do that? How do I get all of them? Is there a pattern that will help me find all of them? Is it related to this one? And we're going to look at all of these things and how to do this algebraically so I don't have to graph all the time. Okay? So keep in mind, this is what's going on when we solve these things. We're going to use the unit circle to help us with all this. So we can see that there are many solutions, points of intersection. There are 2 solutions per period in this particular situation. One here and one here. And the inverse cosine gave me this first one right there. That's pi over 3. So we got to figure out what is that one over there then. What are all these over here? All right, because we know the graph is related to the unit circle, how can we use the unit circle to help us get all the solutions? That's the key here, because that's how we're going to end up doing solving equations. So let's take a look at this thing. I'm going to lay it all out for you so you can see how it's done. And walk you through this one. So what I usually do in solving this thing is I look at this and I think about on the unit circle, okay, on the unit circle, where is the cosine equal to 1/2? So that's a positive 1/2, so that would be 1 up here. There's that pi over 3, okay? But there's also one down here in quadrant 4 called 5 pi over 3, okay? And so anytime I go, every time, it's because it's periodic, every time I go around the circle one time, I pick up answers in those 2 locations for coterminal angles. So pi over 3 is a solution. If I add 2 pi, I have another solution. If I add another 2 pi, I got another one, and so forth and so on. If I go in a negative direction, I get, every time I land here, I get a solution. That's what all these solutions up here are. I have this one, and if I subtract 2 pi, I'm going to get that one. If I add 2 pi, I'm going to get the one that's going to happen right here. Okay? And so, same thing with the 5 pi over 3, which is, by the way, that one. See, in quadrant, this is quadrant 4 right here. And this is the 5 pi over 3 angle, really close to 3 pi over 2. See, it's really close to 3 pi over 2. And that's how you can do those. Once I have a solution, I look at these multiple solutions that I might have on the unit circle, and I ask, can I condense them? And what I mean by condensing them, I'm asking, are they exactly halfway across the circle from each other? So then I can repeat an answer every half circle, okay? Or even, are they condensed even more than that? Usually we just do half circle condensing. These are not condensed that way. There is no equal number between them. I can't take this, add a number, get this, and add the same number to get back to here. It doesn't work. So when that happens, I can write each solution separately. It's this angle, plus or minus 2 pi, that's the period, and n is a counter of how many times I go around the circle. 5 pi over 3 plus or minus 2 pi n, and that's how much I need to get back to another answer, is the 2 pi, and this is my counter, and this is how you will display your answers. These are all coterminal. This here generates all the coterminal angles to these 2 solutions. Okay. How do I solve trig equations? Here's the breakdown for you real quick. Use algebra techniques and/or trig identities to get a single trig function equal to a number. Okay. A single trig function equal to a number. Draw and identify a solution angle in the quadrant or quadrants on the unit circle. For all solutions, It's each solution angle plus or minus 2 pi n. For sine, cosine, secant, and cosecant. For tangent and cotangent, it's the solution angle plus or minus pi times n, because remember, cotangent and tangent repeat every half circle. If we can condense answers, we will. This will change the plus or minus 2 pi n or plus or minus pi n, depending on the situation. So depending on the situation, it will change what this looks like, and we'll talk about that at a later date. There's another type of solution kind that you're going to be dealing with, and that is if I want only the solutions in an interval between 0 and 2 pi, usually is the interval given. When that happens, all you're doing in this case is you're just making a list of answers. There is no plus or minus thing on the end. This gives me all solutions. If I want to restrict my solutions to 1 from 0 to 2 pi on some interval, then I only want the solutions that are in that interval. Okay? And so that's what we're going to be doing. So let's go do some and see how this is all worked out with several examples. So here's the first example I'm going to give. Let's solve the tangent of x equals the square root of 3. Okay? So you go to the unit circle. I always draw a representative unit circle over here to help me visualize my solutions. I want a positive answer, so you need to, hopefully you figured out already that the tangent is positive in quadrant 1. All the trig functions are positive in quadrant 1. And it's also positive in quadrant 3. The reason why it's positive down here is because, remember, the tangent is sine over cosine, and both the sine and the cosine are negative here, so it turns into a positive solution. So I have an angle in here somewhere, and I have an angle down here somewhere. Now, I don't know where it is. We can think about it here in a minute, and we're going to figure it out. Since I know this is the sine over the cosine, how do I know where the square root of 3 is going to go? I always do it this way. We know at the 45-degree angles, or pi over 4, the tangent's 1. So the other ones, as you've done your unit circle, one of them is going to be the square root of 3, and the other one's going to be 1 over the square root of 3. So either the pi over 6, the 30 degrees, is this, or the 60 degrees is this. And the way I usually determine it is based off the coordinate points, which one has, since the square root of 3 is on top, which one of these has the square root of 3 over 2? Well, in other words, I want a square root of 3 over 2, and the other one's going to be the 1/2. So which angle has the cosine 1/2 and the sine square root of 3 over 2? And that's at pi over 3. And so the other one is halfway across the circle from that, which is 4 pi over 3. So those are my two solutions, and you can see as they are equally spaced across from each other, half a circle, I can condense those. Okay? So if I didn't condense them, I would write it this way. X equals pi over 3 plus or minus 2 pi n. X equals 4 pi over 3 plus or minus 2 pi n. And I would write both of those, where n is 0, 1, 2, ... But I can condense these into a single one because they're halfway across the circle from each other. And for that case, you just simply take the first one, pi over 3, and you're going to do plus or minus, and half a circle is pi. So it'll be pi times n. And that picks up both of those. And again, you need your counter. And so then that picks up both that one, add pi, gives me that one, add another pi, gives me back to the coterminal, and so forth. So I just need to add pi to get to each one. So when we have halfway across the circle answers, we will condense them into a single one over here. Okay? And we're done. That's the solution right there. Let's look at another one. The square root of 2 times the tangent of x times the cosine of x minus the tangent of x equals 0. So we need to get single trig functions equal to a number. So to start with that concept, it's all about looking at this and saying, can I factor this? They both have a tangent, so I can factor out the tangent of x. What I have left is the square root of 2 times the cosine of x minus 1. Since now I have a product equal to 0, I can set each of these factors equal to 0, thereby, and I'm going to solve this for cosine at the same time, satisfying the trig function equal to a number. Okay, this is factoring technique that you learned in Algebra 1. This right here, if you did not recognize it, learn to recognize this also as the square root of 2 over 2. So now you have to do the same thing we did for both of these. So for the tangent on the unit circle, when is the tangent equal to 0? Remember, tangent is sine over cosine, so I need the sine to be 0. And that's going to occur right here in these two angles at 0 and at pi. Over here, we have the cosine is the square root of 2 over 2. So where is the cosine positive? Well, cosine is positive in quadrant 1 and quadrant 4. The square root of 2 over 2 is the coordinate you would get for 45-degree angles, or pi over 4. So the first one's at pi over 4, and the second one is down here, and that angle is 7 pi over 4. So I have those two answers right there. So to write my final solution is I have a solution from this one, and I have a solution from this one, and you just put them all together. So the solutions are going to be from this one, x equals 0 plus or minus pi times n. I don't need to put the 0 in front. You can, but you don't need to. And then from this one, I have x equals pi over 4 plus or minus 2 pi n. And then this one, x equals 7 pi over 4 plus or minus 2 pi n. And n is 0, 1, and 2. You need the counter, by the way. Please don't forget the counter. And that's your solution. Okay? What happens, though, if I have, this is cosine of 2x plus the cosine of x equals 0 on the interval 0 to 2 pi. So now I have a restricted interval. I only want the answers in this interval. So this is going to change how I write my answer a little bit. Not how I find my answers, but how I write my answer. Everything up until the point where right before you write is exactly the same. All right? In this case, I have an angle that is different than this one. You have to have the same type angle in the entire problem, unless you can factor it out, which I cannot. So I'm going to need an identity that will help me change this into single angles, not a double angle. And so you can choose any one that you want. Try and choose the one that will most benefit you. I chose this one right here that has only the cosine in it. Plus, it gives me a quadratic action going on. So that right there, by definition, is that right there. And then I can rewrite this into quadratic form so that I can more easily factor or use the quadratic formula for it. So this right here can factor. It'd be 2 times the cosine of x and the cosine of x, a 1 and a 1. I need this product to be plus and this product to be minus. So match that up. So now I have two factors equal to 0, so each one gets set equal to 0. So I end up here for this one, I'll get the cosine of x equals 1/2. And for this one over here, I'll get the cosine of x equals -1. And then we just do the unit circle for each one of these. Everything is exactly the same, no matter which way I solve it. The cosine is 1/2 at this angle and at this angle, at pi over 3 and 5 pi over 3. This one is -1 in only one angle, and that's at pi. So on an interval, all three of these angles are in that interval, so that is my solution. And you just simply list them. So x equals, and no particular order matters, pi over 3, 5 pi over 3, and pi. And that would be my solution. It's just a list. Okay? Let's see. So that's what we're doing in this first video. I'm going to do a two-parter. The next video is going to be about multiple angles. And we'll do that one next.